you, Prashant, and also thank you, Venki and Praveen, for the invitation. Yeah, I will be talking about the exact controllability for a problem using Hilbert Uniqueness Method. So the brief outline, since this is a very heterogeneous group from different specialities, I will briefly describe in my first half of the talk about the Hilbert Uniqueness Method, and the second half will explain you about the problem. So this attribute, of course, to Vasu, a personal loss to me. Okay.
I request the participants to please mute your mics.
Okay. Thank you. Yeah, so let me go to that one. This is the recent joint work with Sar Monsuro and Carmen Perugia, and probably it's already come in applied maths and optimization. So just quickly tell me before coming to the Hilbert Uniqueness Method. So we'll typically consider PDE problems in omega 1 and omega 2, where omega 1 contained in omega with an interface problem. So it's an interface problem with the appropriate interface conditions. And the controllability will be applying controls on neighborhoods of omega 1, which is also a neighborhood of omega here, and also neighborhood of omega 2. On both places, we need to apply control. Of course, there are some open problems where can we get controllability by applying only on the region omega 1. We'll come to the problem later. So let me briefly tell you about the Hilbert Uniqueness Method. And there are various motivations how to introduce Hilbert Uniqueness Method. But let me begin in similarity with the linear control system from ODE. A linear controllability system looks like that with control here. So basically you want to find control U such that it takes the system from Y0 to any other point Y1. If that happens, if you can choose such a U, then you call this system controllability. But in finite dimensions, this controllability can be given in terms of Kalman condition, which is based on the same dimension of certain matrix. Definitely that's not suitable for our PDE analysis. But then this controllability problem can be equivalent to an observed system where it's an uncontrolled system. So basically you have an uncontrolled system and with an observation. Observation is basically a partial information. So from a partial, you observe certain quantities related to your actual state for sufficiently large time. Can you get back your Z? In other words, it leads to an estimating Z in terms of this partial information for in a large time t. And that is happens when you say that it's an observed system. So the controllability can be is equivalent to observability of uncontrolled system, and there is no control as such you see here. Okay, so the controllability reduces to an uncontrolled system, an observation, and an estimating the state in terms of the observation. And of course, an ideal procedure for PDE. Okay, so with that, so let me go to the basics of what is Hilbert Uniqueness Method. You can define Hilbert Uniqueness Method for various systems and fourth order systems, other PDEs, etc. So, but let me take the most easiest one as far as this is concerned. That's a linear equation, and we put the control V on one part, not the entire part. Only we are putting the control on a gamma naught. Of course, you may not achieve controllability if you choose gamma naught arbitrarily. We will tell you some, at least some regions where controllability can be achieved. So, of course, you can also have a distributor control instead of boundary control. You can have the control, which we will see in our problem. Both we can have it, depend on that your choice and other things will be changed. So the controllability problem is to given data starting from initial data Y0 to Y1. Can you choose a control here V so that the solution reaches to the state Z0, Z1 at time t? That's a well-known thing. If such things are said, we say that it is controllable. But in a linear system, the controllability is enough to study when the final state is 0, 0. But that's not true when you deal with a non-linear system. So the control is, if it's controllable only to 0, 0, that means the state y0, y1 goes to 0, 0. That's called controllable, null controllable. And if for this linear system, the null controllability is equivalent to controllability. So the questions in any controllability problems are whether a given system is controllable. If so, find the control and controllable space and time, controllable time, whether to apply control on the entire boundary. So you can ask several questions, and is it enough to apply on part of the boundary? Okay, and find the optimal. If there is a controllability, then you find the best control, optimal control, according to some kind of criteria like energy minimization. Okay, so let me just want to cite one interesting paper, quite old paper in 1992. Of course, the proof of this paper is a bit hard to read because it's a lot of micro-local analysis used there. And it's he has given some geometric sufficient conditions, Bordeaux, Lebo, and Roche. So suppose this is a region where there's you are applying control, and what that paper essentially tells you that if there are some rays which goes and hits the boundary and reflects back, and then it will go on getting reflected back. And once you take any ray, within time t, it should reach the control region. If there are such rays are called trapped rays. So you are applying control almost every place except a small region here. And if there are some trapped rays which never reaches the control boundary, and then such you cannot achieve control. So it's basically tells this paper that you have to control, you have to choose. So in this particular region, if you choose a arc which is more than a semicircle arc, then controllability can be achieved. For example, if you have domains with perforations too, so the domain is domain minus these two holes, and if you don't put these also part of the boundary, and if you don't put control here, you may not get exact control. So you need, otherwise, because there will be a trap. If you don't put control here, there will be a trap. So that's a very nice paper given in the early thing. So there are approaches like semi-group approach. This basically subjectivity of certain operator. It's more of an operator way, functional line of an operator way do. But the Hilbert Uniqueness Method is more interesting to us personally because this only uses PDE techniques, congruence type uniqueness theorems, all that. It's basically a multiplier methods we use. So it's a purely a PDE analysis. So let me follow the similar line from the ODE. You have to consider a uncontrolled system. So now controls with some initial data. So basically how you choose this initial data and how you make an observation and use it as a control and what it leads to. If you look at the ODE, you will see you choose the control in terms of the solution of the uncontrolled system. So we have introduced an uncontrolled system here, and corresponding to that, you say that a reversible system, but it's in a wave equation, this is fine, it's similar, but in a heat equation, because you have to use appropriate adjoint operator. So the conditions are at psi at t equal to, so the end conditions, that's why we are looking for null controllability. So for the adjoint system, we are putting 0 and you are choosing V. So the idea is to choose and make an observation based on this uncontrolled system and use it as a control. And then you have the variation of, you have a choice of phi0 and phi1 varying in some space. So the question is that analogous to the case of ODE, 2 and 3 can be referred to as an observed system. Here the boundary control V is the observed quantity which has to arrive from the solution phi of 2. So can we choose V in terms of phi suitably so that psi also satisfies your initial condition? Look at this equation. So your idea is to choose V in terms of phi, and then there are various types of V. You can make any kind of observation, or you can also vary phi0, so that for one choice at least of phi0, phi1 and an observation, can we choose V so that V also, in that case, the null controllability problem is solved, because in that case y equal to xi, and the control will be the choice of the observable quantity. So that's the whole thing. So there is no controllability, control equations you are dealing with. You are dealing with the two uncontrolled systems. So the question is it possible to vary phi naught and phi 1 in a suitable space and v vary in some other space, so that psi 0, psi t 0 covers the entire controllable space? So you have a variation of phi naught and phi 1 and the choice of v in terms of phi, and then this as that varies, this should vary, it should cover the entire controllable space. Then in that case, observing a quantity related to phi for sufficiently large time can be recovered all the initial state. That's a basic idea about the Hilbert Uniqueness. So partial information for large time propagate information to all states. In nutshell, you can tell that one. So what is the quantity to be observed? What is the corresponding estimate? And a natural choice is then. So maybe those who are not familiar with it, you may think that why this is the natural choice. And this, as I said, you can actually motivate this natural choice in terms of what is called a penalization method, etc. But that requires some more time, so I won't do it here, because once you choose for a control, why not choose for the best control? So it leads to certain optimal control problems. And then that optimal control problem is not well posed, and then you put some penalization, do some analysis, you can see that this is the one choice. Another reason for this is why it's a natural choice, because this is what you are an observer, you may be standing outside your domain and you look at the rate of change of phi. That's one thing. You can also observe phi at the boundary. Okay. So there are various choices, and depends on what kind of control problems I choose. So consider, and another thing, of course, for PDE analysis, when you do integration by parts, you will see this is the quantity, how to do that. So there are various ways of see why this is a kind of a good choice for this problem. So you are putting from phi naught phi 1 and solve that uncontrolled problem. You take your control as dphi by d. You see, now this first, so indeed need to understand, there are some issues now deal with when you start with your phi naught phi 1 in the normal weak formulation, phi in spatial variable like an H1 space, and that you will do basically 1.5 regularity at the boundary, because this is something like grade phi dot nu. So you will lose 1 in the interior and then half in the thing. So you can, in general, you immediately get in the spatial direction H minus half. But so there is what is called a hidden regularity. So normally, immediately when you study wave equation, you don't see this regularity, but you can see that there is a regularity, and you can show actually show that dphi by d nu is in L2. But even with that L2, this problem is not in the standard weak formulation, because you need something like H half, which you don't have it. So you have to interpret this solution. So the first difficulty you face is to interpret this solution not in the normal weak formulation. You have to interpret it in what is called a transposition method. So you have to have the test functions coming from not the immediate space. You have to come from some adjoint system. So that's a transposition method. That's some of the difficulties which you have to overcome while dealing with it. But whatever it is, in principle, what you want to do is that given phi naught phi 1, you define an operator, because by varying phi naught phi 1 and making this choice dphi by d nu as your observation, and then you solve for psi, and you want to see that psi 0 is equal to y naught and psi t 0 is equal to y1. So you want to see that as by varying phi naught and phi 1, this covers the entire thing. Typically, you want to show that lambda is an isomorphism under this thing. So if you want to show that lambda is an isomorphism, first you have to compute. When you compute this, of course, this is the one. But then you do your normal integration by parts and other thing. You can see that this is equal to this one. So this immediately shows that if you want to do isomorphism, you have to show that this is a norm equivalent to the no mean in the standard no mean H1 not of M. This will prove the exact controllability in this very, very weak space. So you get the controllability in an extremely big space, L2 cross H minus 1, because you are getting this an isomorphism here. Okay, so that basically you want to estimate this thing in terms of thing, because this is only an information at the boundary or even a part of the boundary. That's all, not entire boundary even. So that we need to show that there are constants. It tells that this is what I said is a hidden regularity. So you are estimating this L2 no in terms of this energy, preserved energy, because the linear wave equation, wave system, and energy is preserved. And this is always true. The second inequality is always true, but then the first inequality is known as the control. So basically, you are taking a system. So you see the whole control problem reduces to deriving this estimate. Finally, you are not even dealing with anything. Okay, so you take a phi naught phi 1, and in that one solve it and derive this estimate. So that immediately this is called observability and finite. Of course, this is not true in general, and it depends on the controlled region of the boundary and largeness of the time. Both you need it. So second inequality, as I said, is a hidden regularity, but it's always true. Okay. So let me quickly finish this thing. So the beauty is that the controllability problem reduces the thought of estimating terms related to the solution of an uncontrolled problem, which also produces the control. The method, the interesting thing is very numerical. The method is algorithmic and hence constructive. Numerical schemes are available. The inequality shows that this is a norm equivalent to this norm, and that gives you your uniqueness result. So dphi by dv equal to 0 on sigma naught implies phi naught if phi1 equal to 0. That implies, so there is a complete recovery of phi from here. That's what the uniqueness means. So in finite dimensions, etc., the ODE system, and you can see that kind of uniqueness is equivalent to observability estimate, but in PDE systems, observability estimates is stronger than the uniqueness results. Okay, so in a nutshell, so why I said it's an algorithmic. So you are starting with your initial data here. You want to reach final data, outside one. So you solve this operator. Now you know that it's a surjective. So you can solve it for phi naught phi 1. That's your initial data. And once you know the use phi naught phi 1 not to solve phi, and then compute dphi by dv on sigma naught, and then solve for psi. Then psi is your solution. Okay. So the control is dphi by dv, and y equal to psi satisfies this final condition. And so it's enough to establish phi, not true for arbitrary data, what I commented here. So let me a couple of slides more before I go to my problem. So I just want to introduce this also a little bit geometrical, some sort of domains where the above controllability, observability estimate is true. I told you this is not true in general. If you take the gamma naught, but you choose gamma naught in such a, you choose any arbitrary x naught. This gives you various domains, not just one domain. You can vary x naught anywhere. So if you take x naught and choose gamma naught, and this one, which instead of thing, it's better to understand geometrically. So if you have an x naught, you can think x naught as an observer. So if you have a domain like this circle and x naught is at the center, and then you can see that your gamma naught is entire gamma. And on the other hand, if you choose x naught outside, and then you draw your tangents here, and this dotted region is your gamma naught. So you can somehow interpret in such a way that in these particular cases, in any case, is according to the observer, the controllability region is which is concave to you. Of course, you have to see that because we always work with the external normal. Only an outsider can see the boundary, not an insider. Okay, you cannot see the boundary from inside because always external normal we consider. So for x naught, this is completely concave. So you here, so you are precisely applying control where you don't have the visibility. In this particular case, you can interpret that way. So if x0 is an observer outside, you draw the tangent. This is convex to this observer, and this is the dotted region is where you are. It's not visible to this observer. So you see, if x0 moves far and far away, if this tangents moves towards the center, but it can in tune with Bardo's paper. So you always get a little more than your semicircle. You see, when the x0 goes to infinity, you get this parallel thing till that time. So you have your controllability region little more than minimum. So when x0 moves far and far away, it's enough to apply control in a smaller and smaller regions, but then you have to pay a price. Controllability is, you see, the controllability time comes from this maximum. So x0 goes more, r0 goes to infinity, and t0 goes to infinity. So on the least will come, if I remember correctly, when x0 is here, but then you have to apply control everywhere. So it's a trade-off between you want controllability immediately, or it's reasonable to apply control in sometimes the regions may not be reachable, right? Certain boundaries you may not be able to apply in practical cases. So that's a yeah. So is there is so this is what I interpreted. This page is the one I interpreted, and then so let me go to now. So there's another work also with the boundary controllability, but what I'm going to do instead of boundary controllability, what I'm discussing here is about the internal controllability. Okay, applied this one. This is so this more important work from here. Only some estimate proving in the second paper. That's little not that difficult from here to here. So this is two domain. This is the gamma interface domain here, and you have the control region here. You have control region here. What we are still not fully happy with this work is we want to get rid of this control region, and we feel that because it is a nice interface, the information should reach here also, but then when you look at the estimate to be derived, that's not immediate. Probably you can work more on that. So that's a kind of open work. So we are typically doing this wave equation again with the general second order operator. Now I am putting an internal control. So you zeta 1 is the control applied only in omega 1, and I'm also applying control zeta 2 on omega 2. And this is a standard, this imperfection problem is studied with, not for the controllability, for the is already available without control. So it's a weak formulations, and that's there are many interpretations of that. All are available. So you have your interface conditions, and sigma 1 is the interface, gamma 1 cross 0 to t. So you have the interface condition. So it's typically it's a wave equation on both sides in omega 1 and omega 2 wave equations. This is the characteristic function. So you have the theorem what we have proved in this result. So these are the some weak spaces. So for any initial data in this space, H gamma is a typically H1 space. But since you have the boundary condition, so you have the boundary zero boundary condition only on the outside boundary interface, you don't have a zero condition. So just you have to define H1 space with that. So that is one. But so that you see, this is something like already you have seen L2 cross H minus 1. So you can think that this is something like that. And then here is a control. That is this is a much weaker space. You will see that. Control in zeta in omega prime. So you can achieve the controllability. That's a result of this paper. But I will show you some steps in the what is my controllability estimate to be proved. And I will end the talk at that stage. So these are the spaces you see. So on the omega 1, you have the outer boundary condition. And this we are writing in this form because it's 2 PDE problems in 2 different domains. And B2, you don't have any boundary. And you have to take care of the interface condition. You have that. These are all not, well, according to the problem, you define, and it's already there available. So you define this math. On the W, you define that. Okay, and the control space is W prime. So you see, so W you can think it as somewhat like something like L2 cross H. The to T is L2. So other cross, this is something like H2. B is also like H1, except for the boundary. And this, so the control is coming from W prime, and the controllable space is this one, somewhat similar. Okay. Since the controllable space is very weak, as I told you, which is also the initial data space, we need to seek solutions in the sense of transposition, and that's available. So this is already explained in the general situation. So the controllability means given U0, U1 and Z0, Z1 in these spaces, find a control satisfying this one. So we do it in the equivalent to null controllability. So the procedure is, since I have explained in detail about the Hilbert Uniqueness Method, we only need to know what is the estimate to be proved. So you start with your homogeneous system. So you see homogeneous system now controlled here on each of the domain. And then that weak formulation is quite standard once you know that one. Do the integration by parts and you get your weak formulation, and existence is also known for that. Okay. And then the adjoint system. So adjoint system, you can see the sort of observe, this is your observation now. So from here, Z, this is your observation, which is quite weak, and you can interpret it in the W prime thing. So you haven't, yes, some disturbance. Okay. So, okay.
I request the participants to mute their mic, please.
Okay. Anyway, not major.
Yeah, go ahead. Go ahead. Yeah.
So you have your control here, which you interpret it, and then this is the control form, and the null controllability problem is solved if theta satisfies this. Okay. Thus, the key point is to choose the initial data so that the above initial conditions for theta are satisfied. This again motivates. So if you understand the Hilbert Uniqueness Method, now it's a pretty clear what to be proved, or what to be, which operator to be defined. So you have lambda like this, Z0, Z1 equal to this one. And then if you can solve this equation, lambda Z0, Z1 equal to this one, to obtain suitable initial data Z0, Z1 to establish the controllability. In fact, we prove that lambda is an isomorphism. So you compute this again, exactly what I said. Once you compute this one, this is the data, you get it. Okay. So this is the norm which you have to show that it's actually a norm. So to keep it in mind that this is defined in omega 1 and omega 2. Though I have given the entire boundary, actually you don't have to choose omega 1 as the entire boundary. You can choose some part of the boundary, but not something very arbitrary, similar to I have defined with that geometric condition. So you don't need really omega 1 and omega 2 entire boundary. But my open problem is not that one. Open problem is something I want to get rid of this term at all, completely. You will see that soon. Okay, but so though I have stated here omega 1 fully, you don't need it. You can choose various subdomains of omega near the boundary. That's possible. Okay, so then you have to choose. This is an isomorphism. One, inequalities of equivalence is the direct estimate from the homogeneous problem, and the lower estimate is your what you call it, an observed inequality. Okay, so this is your control. You will conduct, and which is an element here, which can be interpreted. And then you look at your energy, exactly what you have seen it. You have to include these terms here. You look at your energy thing, and you can prove that energy is conserved. You get that one. So you look at its values at the origin. And this is your, so we have the following lemma. So the first lemma to be proved, which is a major lemma. From here, you will need to have another step. So you prove essentially like an observability. Please keep this in mind that not exactly that one. You want to have it. So you will do this estimate in 2 steps. So you see, you have Z1 here, Z2 here, but at the first level, you prove the, and this proof it involves some multiplier methods and some identities, etc. to be proved. And so the one major step you eventually prove is that you have to prove this E0, which we consider. This is a standard type for this problem, if you look at the energy. So you have to prove this estimate is 0. First step, you prove this estimate. And once you prove that estimate, and then the observability estimate is E0 less than or equal to C1 of t integral of this one. So that's what, of course, there are some conditions and that are also certain conditions we have. There are some geometric conditions. As I said, that's also we are not fully happy to prove that one. We want to get rid of some of the conditions there which restricts the domain, some star shape, etc. But so far our analysis, we are not able to see that one. But I see that are all more of technical reasons. It's not practically that condition should not come. But unfortunately, there are some conditions which prevents us to do it. Some technicalities. Maybe more work to make to this one. So you will have your observability estimate in terms of your. So this is so you say, so you have your equivalence of the nodes. Of course, this is a standard direct estimate, as I said, which also requires some identity to be proved. But then that's a kind of direct thing. And this is the where, yeah, so there is a constant. So you have this equivalence of these nodes. I'm nearly to the end of my talk. Maybe I have gone little quickly. So maybe we can spend more time on it. So you see, this also leads to what is called the equivalence of standard norm in H gamma with this norm. So you have your norm here, and this is an equivalent norm there. So here you see when Z1, Z2 equal to 0, and all this is 0, you get that one. So you get the entire information by knowing your Z1 in omega. And that leads to exactly again the uniqueness results. You see, when Zi equal to 0 in omega y cross 0 to t, then Zi equal to 0 in omega I. So you have your thing. I didn't add the kind of proof because now if I want to have any proof in this part, the identity proof, etc., a bit longer. Those who are in exact controllability or gone through this one, most of the terms will be familiar, but there are terms which we have to overcome. And but stating itself will take unnecessary time. So I think I will stop here. Thank you. Thank you.